to you all and welcome to GOE Academy. It's an academy which means God over everything, where we bring success to your doorsteps. So let's get started into what we have for you guys today. So this video comprises of Faculty of Science, experiments involve your biochemistry, microbiology, applied botany, applied zoology, environmental sciences, and biomedical sciences. The course title for this material is Mathematics of Biologists. The course code is MATS2108. Always know your maths code. Okay? So our main focus for this chapter 1 was indices, logarithms, and exponential functions. Part 1 of it was really treated on indices and logarithms. So if you haven't watched that video, make sure you go and watch it before you come back to watch this one, because it's just a continuation. So in this particular session, we are going to look at the part 3 of it, which is on exponential and logarithmic functions. Okay, so let's get started with a brief introduction. What is an exponential function? Let's consider this case. Okay, so if we consider a function of the form f of x equals to a raised to the power x, where a is greater than 0, note that a can be any number, say 1, 2, 3, 4, 5, 6, and so on, a half, and so on. A function of this form is said to be called an exponential function. The principle of exponential function is based on several different cases. So let's look at the first case. The first case occurs whenever a is equal to 1. So if a is equals to 1, then from our general formula f of x equals to a raised to the power x for exponential functions, if we replace the position of a by 1, then our exponential function become 1 raised to the power x, which is equals to 1. You need to know that 1 raised to the power any number will always give us 1. 1 raised to the power 100,000 is equal to 1. Okay, so to this effect, this leads us to a function known as a constant function. Okay, so case 2. So let's look at case 2. Case 2 occurs whenever a is greater than 1. If a is greater than 1, then what are we trying to say? We're saying that a can become 2, 3, 4, 5, 6, okay, and so on. So from f of x equals to a raised to the power x, what happens? Let's say, for example, the value of a is equals to 2, then f of x equals to 2 raised to the power x. We have just replaced the position of a by 2. Okay, now if a becomes 3, then the function becomes if a becomes 5, then the function becomes 5 raised to the power x. If it becomes 3, it becomes 3 raised to the power x. Okay, and so on. So functions of this form can easily be sketched. Okay, can easily be sketched. So we're actually going to look at a few examples in order to understand how to sketch or draw exponential functions or representing them on a graph. So let's look at this first example. If we're asked to sketch the function f of x equals to 2 raised to the power x, how do we go about it? It's very, very, very simple. So please, before I solve this, I want to make a remark. I want you to pay close attention to the solution, because after this first example, the other examples that will be coming up will be similar examples, and I will not explain detailedly for reasons which are very, very important for you, because especially when we come to data issue, if the video becomes too long, it will be difficult for you to watch. Okay, so we want to make it short and simple. So please pay attention and understand this. I'll explain this detailedly. For the other examples, I will not go detailedly. So how do I sketch an exponential function? For me to sketch a curve, I need to get is what? The coordinate values, and the coordinate values must be within a certain scale. Okay, so I can decide to choose my range of values of x to be from 0 to -2, or from -3 to 1, or from 0 to 1. The fact is that you need at least 2 values. You need at least to have at least 2 points to plot before you can sketch a curve. At least 2 points and above. But I always advise my students to at least get at least from 3 points, so that you get the exact curve. Okay, so after getting my range of values of x, let's say I want to plot from -2 to 2, or from 0 to -2. What I do is I have to substitute those values of x in my exponential function in order to get the corresponding values of y, or f of x, which is simple. So let's apply this. Our function is f of x equals to 2 raised to the power x. So let's take the first case where x equals to -3. I've decided to choose my interval to be from -3 to 1. So if x equals -3, I replace x by -3. Simple. So I end up with 2 raised to the power -3. And you punch in your calculator, you end up with 0.125. Same thing, when x equals -2, I substitute in my exponential function. I have 2 raised to the power -2, which is 0.25, right? And the same thing goes for -1. Just punch your calculator. Now, when x equals to 0, I'll have 2 raised to the power 0. From our previous videos on lots of indices and logarithms, we saw that any number raised to the power 0 is always equals to 1. So 100,000 raised to the power 0 always turns to 1. Okay? Some people will be asking why I like calling 100,000 a lot. Okay, so for x equals to 1, we have 2 raised to the power 1, which is equals to 2. So to plot or to represent this on the graph, it's good for us to put our coordinate values on a table like this to make it look presentable. Okay, so to plot the corresponding values of x, if we do that, x and y, if we do that, we are going to have a curve of this form. Okay, so now please pay attention and see how I'm going to represent these values of x and y in order to come out with this beautiful curve, as you can see in blue. So the very first thing, observe and see that the first value of x on my table is -3, right? So I simply go to my x-axis. I've labeled it the x-axis, and I draw a vertical line on -3. The corresponding value at -3 is what? 0.125, which is on y. So I go to my y-axis and I draw a horizontal line where I have 0.125. Observe and see there's no 0.125, but you have to extrapolate. If you extrapolate perfectly well, you see that that will be the position of 0.125. And observe and see that those first points, they meet at a certain point here. Okay, that's why I have my point here. That's my first point. Okay, so I go to the second value, -2. When x equals to -2, I draw my vertical line. The corresponding value of y is 0.25, right? So I go to my y-axis and I extrapolate. So 0.25 is just like half of 0.5, right? Kind of. So it should be somewhere around there. So that's it. And where the intersect, that's where I have my point. I go to the next. When x equals to -1, I have my vertical line. The corresponding value of y is 0.5. I have it at 0.5. You see where the intersect? I place my point there. Next, when x equals 0, what happens? The corresponding value of y is 1. That's it. So it does not move towards the left or towards the right. You just add 0. So we don't know, it does not move on the x-axis towards the left or towards the right. So it remains vertically. Okay, so that's the position. That's why I just have my point at what? At 1. Okay, I just have my point at 1, which is simple. I just have my point at 1 here because it does not move towards the right or towards the left. So I just have my point here. And note that the point, if x is instead 1 and y is 0, the point will be somewhere here. Okay, it's just a reverse kind of process. If x now becomes 1 and y is 0, the point will now be here. If x is 0 and y is 1, the point will be here. Okay, here. So what happens when x is 1? I have my vertical line and y is 2. I have my horizontal line along the y-axis, and that's where they meet. Now what's the next thing? The next thing is for you to link these points. All of them together. Now how do you link these points? You need a broomstick, or you can use a piece of thread. Okay, you place it carefully along the points and you link it. Okay, sorry, I'm not actually going to do it perfectly well. So you link it carefully and you end up with something like this. Okay, so this is how you actually plot your values of x and y on a graph. Hope it was well understood. Okay, so let's proceed. Let's look at this other example. Plot the curve f(x) equals to 5 raised to the power x. We follow the same approach. You get your coordinate values, you substitute them in order to get the corresponding values of y, or f of x. So when f when x equals to -3, corresponding value of y will be what? 0.008. So you just 5 raised to the power -3, right? We replace the position of x by -3. Same thing when we have -2. Same thing when we have -1. You just punch in your calculator. Now we have 5 raised to the power 0 when x is 0. Anything raised to the power 0 is always equals to 1. 100,000 raised to the power 0, we have 1. When x is 1, we have that. So we can represent this on a table to ease our plotting. Okay, so it is simple. So that's the table, this is the graph. You just need to do the same thing as we did in the previous exercise, and you end up with something like this. Okay, so observe and see that the previous curves we have plotted are curves of exponential functions of the form a raised to the power x. So any exponential function you have, as far as a is greater than 1, will always have the same shape as the previous curves. Let's say we have 10 raised to the power x, 6 raised to the power x, 7 raised to the power x. All of them will take the same shape. So please, if you have actually been following up, as we move forward with the following exercises, you can always pause the video and try to answer the question, and then you come back and replay the video and compare with my own answer for better understanding. Okay, that's just like to know if you're actually following up. So let's proceed, please. Let's look at this other function. If we're asked to plot or to sketch the curve f of x equals 2 raised to the power -x, we follow the same approach. Okay, we follow the same approach. Get your coordinate values. Okay, so first case, so when x equals -3, I have 2 raised to the power -3. Be careful, whenever I see two negative signs together, it tends to become a positive. So this is the same as 2 raised to the power 3, which is equals to 8. So same thing when we have -2, we have 2 raised to the power -2, okay, which gives us 2 raised to the power 2, which is 4. So for x equals to 0, be careful here. Any number raised to the power 0 always give us 1. Whether is as far as it's 0. Know that there's nothing like -0. Okay, so end up with 1. Good. So we have that, we can represent our data on a table, and we plot. So if you plot that curve correctly, you end up with something like this. Okay, so case 3, what happens when a is less than 1? If a is less than 1, then we're talking about numbers like half, 1/5, 3/10, and so on. So let's just look at an example. If a is equals to a half, then our exponential function becomes a half raised to the power x, which is the same as 2 raised to the power -x, right? From our laws of indices, for those who already watched the video. Okay, when a equals to 1/5, we have the same thing. We have 1/5 raised to the power x, which is the same as 5 raised to the power -x. Those are all exponential functions. Okay, so let's take a look at some few examples for better understanding. So imagine we have to sketch the function f of x because we have raised to the power x. You need to realize that this function is the same as what? 2 raised to the power -x, right? So we follow the same approach. Okay, we follow the same approach. Observe and see that this example has already been solved in the previous slide. Okay, it is the same example. A half raised to the power x is the same as 2 raised to the power -x from our laws of indices and logarithms. So it is the same exercise that has been done previously. So mem shows, okay, the same thing. You follow the same approach, and you end up with the same curve. Okay, so we proceed. So let's look at case 4. Now what happens when a is equals to e? So if a is equals to e, then our exponential function becomes what? Becomes simply e raised to the power x. We just replace the position of a by e from our general form, right? Okay, I hope everybody is cool here. Now if a equals to 1 on e, then we have one on e raised to the power x, which is e raised to the power minus x. Hope it's well understood. So let's take a few examples on how to plot curves of that form. Simple. So we were asked to sketch the curve f of x equals to e raised to the power x. It's simple. So the first thing, as we know, always choose our coordinate values, and after those are the range of values of x, and then after we substitute and get the corresponding values of y. So if we have x equals -3, for example, that means we're going to end up with e raised to the power minus 3 if we substitute. And you know that e has a value, and you can punch it as well on your calculator. I think e has a value of 2.72. Yes, you can just take 2.72 raised to the power minus 3. It gives you that answer. Or you can press the value of e on your calculator as well. So if you substitute all of this properly and punch properly, you will end up with these corresponding values. Okay. Actually, the value of e is not 2.72. That's the value of e raised to the power minus 1. Okay. So if we represent that on a table like this, we end up with this. Okay. We end up with this. And if you represent it on a curve, you have a curve like this. And this is a graph of e raised to the power x, right? So automatically a graph of e raised to the power minus x should be a reflection. Of this curve. Okay, it's the same as a graph of 2 raised to the power x should be a reflection of a graph of 2 raised to the power minus x. Good. So good. So a graph of e raised to the power minus x should just be a reflection of the previous graph. That means it should just be in an opposite sense to it. So we follow the same approach. Okay, we follow the same approach, and if you substitute, you have that value. Note that whenever you see two negative signs together, it becomes a positive. Okay, so if we do that, we end up with this. And if you represent this your information on a graph on your graph paper, you end up with something like this, and you see that it is just like a reflection of the previous curve we had, right? So let's look at exponential functions involving ln and log. So we are going to look at functions of the form f of x equals to log x base a. Okay, where a is greater than 0. So if I say, for example, that my value of a is equals to 2, then f of x should be equals to what? Log x base 2. Are we okay? Just replace the position of a by 2. Okay, if a equals to a half, we're going to have log x base a half. Okay, a is just acting as a base. Let's take a few examples for better understanding. So if I ask to sketch the curve f of x equals to log x base 2, how do we go about that? So it's the same approach, okay? The same approach, but here you have to be careful. The way you get the values are a little bit different. So to sketch a curve of this form, we need to choose values of x as say 1, 2, 4, a half, and 1/4. Okay, and then we proceed by substituting the corresponding values of x in our function in order to obtain the corresponding values of y, as we know. So let's look at this. So this is our function. So you need to take note that f of x, if f of x is equals to log x base 2, what does it mean? It means that f of x will be equals to what? What does it mean? It means that x will be equals to 2 raised to the power f of x, right? Or 2 raised to the power f of x will be equals to x. We saw this, how to change from logs to index form. We saw it in our previous video, so you can check it out if you didn't watch it. So this is a concept we'll be using here to plot to get the values. So let's look at this. Observe and see that for the first case, when x is equals to 1, right, we are going to have log 1 base 2 if we substitute, and this means we have 2 raised to the power f of 1 to be equals to what? 1, right? And what does it mean? It means that 2 raised to the power f of 1 is equals to 1, right? Now observe and see that this 1, right, is the same as what? 2 raised to the power 0, right? The same as 2 raised to the power 0. And observe and see that since the bases are the same, we just equate the powers. So f of 1 will just be equals to 0. Same thing when we have f of 2, that's when x becomes 2, we have log 2 base 2, right? And if you transpose to index form, you have 2 raised to the power f of 2, right, to be equals to 2. And any number who does not have a power, you always know the power is always what? 1. And since the bases are the same, we equate the power, so f of 2 equals to 1. Same thing with 4. We have 2 raised to the power f of 4 to be equals to 4. You know that 4 is the same as what? 4 is the same as 2 raised to the power 2, right? 2 raised to the power 2. So since the bases are the same, we equate the power, so f of 4 equals to 2. Same thing here. When we have a half, we have 2 raised to the power f of a half. A half is the same as 2 raised to the power minus 1. Bases are the same, we equate the power. So f of a half equals to -1. Same thing here. We have -2. I believe that was well understood on how to get the corresponding values of x and y. So if you want to represent the data on a table, we have something like this, and if you plot the curve properly, you will end up with something of this form. Okay? So let's look at, if we are asked to sketch the graph of ln x and discuss its properties, what do we do? Okay, so to sketch a graph of ln x, we need to look at the relationship between exponential functions, okay, and we need to look at the relationship between exponential functions, that's function of the form f of x equals to e raised to the power x, and logarithmic functions, which are functions of the form f of x equals to ln x or log x. Okay, so let's look at their graphs. I'll just dive in the graph below and you see. So this is the graph. Now what do you need to know about this graph? You need to know that the graph of ln x, okay, is just a reflection of the graph of e raised to the power x. It's just a reflection. Just a reflection. Simple. Okay? Just a reflection. So you can see straight away that the logarithmic function f of x equals to ln x is just a reflection of the exponential function f of x equals to e raised to the power x. Okay? In the line represented by what? F of x equals to x. At this line where you have broken lines, at that point this line means that what? Y is equals to x, or f of x equals to x. Okay, so the function e raised to the power x is just a reflection of the function f of x equals to ln x, or in other words we can say that what? We have just swapped the axis, okay, or x has just become f of x and f of x has become x. Simple. I hope we all are good. So what are the properties of this function? The properties, first of all, ln x is defined for positive values. That's why this graph of ln x will always be what? You will never see graph of ln x of ln, okay, on this side, on this negative. It's always towards the right, the positive portion, okay, towards the positive portion. So that is the first property it has. Secondly, ln x is less than 0 for x less than 0 less than 1 in that interval. Okay, also ln x is equal to 0 only for x equals to 1. Also ln x is greater than 0 for x greater than 1. Okay, take note of that. So let's look at how to plot or how to sketch a function of the form log x. Now whenever a function is given, okay, without a base, you should know the base is always 10, base 10. And for ln, if a function is given at ln, know that the base is always what? E, base E. I forgot to mention that. So if we want to plot our curve for this, it is very, very simple. Okay, it is very, very simple. Very, very simple. Very, very. We follow the same approach as we did for ln. The same approach. The same approach. So f of 10 is equals to what? Log 10, right? Or let's start from f of 1. f of 1 is equals to log 1, which means 10 to the power f of 1 is equals to 1, right? So f of 1 is equals to 0. Because any number raised to the power 0 is, any number raised to the power 0 is always 1. Okay? So I believe you all can do this. If you understood the previous exercise, then this should be something simple. So my corresponding values of x that I've taken here is 1, 10, 100. Okay? So if you do that properly, even 1 on 10, I also took 1 on 10 as my value of x. I also took 1 on 100 as my value of x, and that was the output. So I can represent this my output on a table. Please, I hope I'm not too fast. I hope this was understood. So it's the same approach as in the previous exercise. So you put the data on the table and plot, you have something of this form. Good. So the properties are slightly the same as those of ln. Okay. So log x2 is always also defined for positive values, okay, of x. So we have log x less than 0 for that interval. We also have log x equals to 0 for x equals to 1, and we have log x greater than 0 for x greater than. Okay. Now let's look at some other examples. You were asked to solve ln x plus 5 equals to 3. Ln of x plus 5 equals to 3. It's simple. You need to know that the ln function is always to the base e. So if you want to change from ln form to index form, it's the same as change from logarithmic form to index form. Just know that the base is e. So normally to solve this, you need to do what? To solve this, you need to do what? You just see that x plus 5 will be equal to e raised to the power 3. That's all. Okay? And the value of x, to make x the subject of the formula, 5 is disturbing x from being alone. So you send 5 the other way, and it becomes negative. When something is crossing an equality sign, the sign has to change from, if it was positive and it's crossing, the sign, if it's crossing and it was positive, the sign has to become negative. Hey, I'm sorry, here is supposed to be 5, okay, minus 5. So we're going to have x equals to e raised to the power 3 minus 5. Simple. So if we're asked to rewrite the following, first one, we have 2 raised to the power x. From our law of exponential, from our law of negative powers, 2 raised to the power x is just the same as 1 divided by 2 raised to the power minus x, right? It's just another way of writing the function. 5 raised to the power x, still from the law of negative powers, is the same as that. 2 divided by 5 raised to the power 5 is the same as 1 divided by 2 raised to 2 divided by 5, all of that raised to the power minus 5. So it's just another way of writing the function. Okay, so if I ask to simplify the following, 5 ln x plus 3 ln y minus ln 4z, all of this just for you to apply the product and division law of ln or log, which we saw already. Okay, so we have 5 ln x plus 3 ln y minus ln 4z is just the same as what? Ln x squared plus ln y cubed minus ln 4z. So please note that There's another law of index that says that this 5 will always come to the power of this value in front of the ln. That's why we have 5 ln x has become what? Ln x raised to the power 5. I'm sorry about that. Here was supposed to be 5. So ln x raised to the power 5. Plus we have 3 has now come to the power y. So we have ln y cubed minus 4 minus ln 4z. Okay, good. So this implies that we're going to have x squared y cubed divided by 4z. Let me explain that step. So sorry, in the place of x squared, it was supposed to be what? X raised to the power 5. Okay, I'm sorry about that, just a typing error. X raised to the power 5. So what have I done here? Observe and see that this is what? This is product rule of ln or log. So product rule says I just product rule. For the product rule, what are we going to have? There was a lot of typing error here. Please let me just solve it up here. So we have ln x raised to the power 5. This ln x raised to the power 5 plus ln y cubed has to become what? Has to become the ln of, since it is addition, that means it's multiplication. Okay, the ln of x raised to the power 5. Okay, ln of x raised to the power 5 times the ln of x raised to the power 5 times, or let me just put dot, y cube. Okay, dot y cube. That's what it becomes. So this guy is the same as ln of x raised to the power 5 plus ln of y cube. Okay, so that's product rule. So minus the ln of 4z. So this is what we should have as our final expression. I'm sorry, there was a lot of mix-up. So I hope everything is okay now. So I'm so sorry for the mix-ups. So we're asked to simplify the following: ln of x raised to the power 3 times x raised to the power 4 divided by 0 to the power 5. We still apply the same product rule. So this is the same. This is just like the reverse of the example that was given previously. So ln of x cubed times y raised to the power 4 will become what? Ln of x raised to the power 3, right? Plus ln of y raised to the power 4. All of that divided by z raised to the power 5. Okay, so it's just